Let's take a look at example 2 on your screen. This problem has a very interesting twist. We have a telegraph wire with an initial length of exactly 100.0 meters, measured at 30 degrees Celsius. The linear expansivity of the wire, alpha, is given as 2 times 10 to the power of -5 per Kelvin. Our objective is to find the new final length of the wire when the temperature drops all the way down to -10 degrees Celsius. Notice what is happening here. The temperature is dropping from 30 degrees down to -10. This means the wire is cooling down. So instead of expanding, it is going to contract and become shorter. Let's find our change in temperature, delta T. Remember, change is always final minus initial. So we calculate -10 minus 30, which gives us a negative temperature change of -40 degrees Celsius. The negative sign simply tells us that heat is being lost. Now, let's first calculate the change in length, delta L, using our standard expansion formula. Delta L equals the initial length multiplied by alpha multiplied by the change in temperature. Let's substitute our values. We multiply 100 by 2 times 10 raised to the power of -5. And then multiply that by our temperature drop of 40. Mathematically, 40 times 100 is 4,000. And 4,000 multiplied by 2 times 10 raised to the power of -5 gives us exactly 0.08 meters. Because the temperature dropped, this 0.08 meters represents a decrease in length. To find our final length, L2, we take our original length of 100 meters and subtract the shrinkage of 0.08 meters. 100 minus 0.08 gives us a final length of 99.92 meters. Looking back at our options, this perfectly matches option D, 99.92 meters. Now that brings us to the end of linear expansivity. We still continue with thermal expansion of solids. Our next topic is superfacial and cubic expansivity of solids.
Udimking Education Foundation. Building confidence, ending examination malpractice for a better tomorrow.
We are building a better tomorrow.
Join us in shaping futures through integrity and education.